Untitled Chapter. It's my pleasure to introduce Richard Kleeman from the Courant Institute, who's going to talk about a class of stochastic samples.
Okay, thanks very much. I'd like to thank the organisers of this program. I've been here nearly 2 weeks now, and I've found it to be a very enjoyable, very productive, and very interesting program so far. What I'm going to talk about today is a particularly simple class of stochastic climate models. So I'll go to the chalkboard first. So the particular type of system that I'm interested in is essentially additive forcing and multi-dimensional system. And what I'm going to assume is that this matrix here, A, is a constant. Okay? That's about the simplest stochastic model that you can think of. But what I'm going to do, which is a bit novel, is I'm going to consider the general case. So I'm going to consider the n-dimensional case. And what I'm going to be particularly interested in calculating is the spectrum from such a system. So take a particular component of a vector from that system and compute its spectrum. So why would I be interested in doing that? Well, firstly, I'm going to spend the first maybe 15 minutes of the talk rationalising why I'm considering such models. And I'm going to do it using 3 examples. Probably 1 or 2 of those are very well known to people. And so what I'm going to argue is that such models are physically relevant. Why am I calculating the spectrum? Well, there's 2 reasons for that. One way of validating these models, and I'll come to this in a bit more detail in a minute, is by actually looking at the spectrum, the equilibrium spectrum of such systems, and comparing it to what you get out analytically, which I'm going to derive analytically, for such a simple stochastic model. And if I can argue that the match with the observations is good, then I'm going to argue that this model here is a good null hypothesis for what's going on with respect to the climate variability that I'm trying to model. Now, sometimes such systems may be good null hypotheses, and on other occasions you may be able to reject such models as null hypotheses. What I'm thinking about in particular here are stochastic models that involve multiplicative noise. And I'm not going to consider those here, but I just want to lay that out. I'm adopting the attitude of a null hypothesis mentality towards such models. Another reason for studying the spectrum of such models is that this is a common conceptual division in climate. So one considers decadal variability, one considers interannual variability, one considers intraseasonal variability. So built into that conceptual framework for looking at climate is a frequency dependency. So if one does a spectral analysis on such systems, then one gains some insight into where power comes into those various bands. All right, so what could influence the spectrum of such a simple system? Well, I'll show you analytically that there are 3 important factors, but you can probably guess the answer before I give you the analytical derivation. The first is that it's going to depend on this matrix A, in other words, the dynamics of the unstochastically forced system. Now, you can consider those dynamics in a variety of different ways. You could consider them with respect to some sort of normal mode basis. One could consider them with respect to a singular vector basis. Whatever. In this talk, I'm going to argue that to look at the spectrum comprehensively, one should really use a normal mode basis. Okay? So that's one thing that the spectrum is going to depend on. The other thing that it's going to clearly depend on is the statistics of this forcing vector here. Okay, I'm not assuming that the components of the forcing vector here are uncorrelated. What I'm assuming is that they have complex covariance structures associated with it. And the complex covariance structures will determine, as we'll see in a minute, the spectral response. So that's the other factor, the statistics of the stochastic forcing. The third thing that's important is which particular component of the vector one is interested in. Okay, this thing here has n components. Which of those n, or which particular linear combination of those n components is one considering and one is trying to calculate the spectrum of? Okay, so those three factors will determine the full solution to this problem. And I'll give you a comprehensive solution for determining the spectrum of any particular linear combination of those components of the stochastic system. Sorry.
Can you just check the mobile phones, as there seems to be some buzz on the audio, so make sure your mobile phones are off. Sorry about that.
This work is currently in review with the Journal of Atmospheric Science. It's been revised once, and but I'm happy to share the manuscript. So if you're interested, I can give you a copy of the manuscript. Also relevant to a particular example, I'm going to apply this particular analysis to a physical case that I'm very familiar with from my past research, and that is El Nino. Okay, and what I'm going to do is propose a new mechanism for decadal variability of El Nino. And I'm going to use this new analytical framework to argue that that decadal variability has very particular properties which you can test in the observations. I haven't done that yet, but I'm just arguing that it's falsifiable, the theory that I'm about to propose. Okay, so let's look at stochastic modelling and some philosophy behind stochastic modelling. This is my personal philosophy towards stochastic modelling. I believe that an important principle in building stochastic models is Occam's razor. One should build a model that is based solidly on the dominant physical mechanisms operating within the system under consideration, and one should be very self-critical in doing that. One should convince oneself that the physical mechanisms that you're putting into the stochastic model are credible, and that if I make certain changes to those under reasonable parameter uncertainties, that the fundamental qualitative results that I obtain won't be affected. And also, I should be able to point very concretely to every piece of that physical model as having a justifiable physical origin. So that's the first principle. The second principle should be that the model should show robust qualitative agreement with the observations with respect to the dominant form of variability being considered. Okay, these seem like reasonable motherhood statements about stochastic modelling. But the third principle is, I think this is an interesting one, is that the model should be as simple as possible, consistent with the first two principles. And the reason I'm doing that is because I want to set it up as a test bed. So I want to say, can I reject the null hypothesis that this model is the explanation for what is happening? So that's the kind of philosophy that I'm going to follow in this talk. Now, looking at principle 3, this is the reason for considering such models as this. These really are the simplest stochastic models. Okay, why would I view those models as influential? Well, you can obtain the unstochastically forced model by linearizing a complex nonlinear dynamical system. And this is a long tradition in geophysical research, a long, important and revealing history. So there's a reason for linearizing the system. Additive forcing, well, that's a little less certain, okay, but it's a reasonable first stab at the problem to add some additive stochastic forcing to the problem. Okay, so do these principles stack up? Let's look at some systems to see whether I can say that systems like that are actually, they actually have physical relevance. Okay, so first system I'm going to consider, and this is the basic motivation of this talk, is Klaus Hasselmann's climate model, which I guess most people are very familiar with. And that, what we do here is we consider heat flux forcing of the mixed layer of the ocean, okay, and we consider temperature anomalies with respect to some sort of climatology, and we build a model of that. I'm not getting this is the model here, and so what this model is very simple. It's just a relaxation model. So I just have some sort of negative feedback here, and I have some sort of stochastic forcing here. This is about as simple a stochastic model as you can possibly get. Okay, is this model physically plausible? That's an interesting question. What do these various things here represent physically? Okay, this one here represents the fact that SST anomalies always have, not always, mainly have a negative feedback with respect to heat flux. So heat flux acts to damp SST anomalies. That you can establish as pretty reliable, okay, a pretty solid hypothesis. What's the stochastic forcing operating within this system? That's an interesting question. Well, if you linearise the bulk relations for heat flux, you discover that there's a term that depends on the wind speed anomaly. And the wind speed anomaly, of course, is subject to wind gustiness. So that's a reasonable physical origin for the forcing term there. So I would argue that this model is physically plausible. Okay, and in fact it's been extremely influential in stochastic climate modelling. So what does the spectrum of such a system look like? It has this characteristic form here, which is known as a Lorentzian form. Okay, so it's got k over k squared plus omega squared. K here is the damping time of the system, and omega is the frequency of the spectrum, which one is considering. The shape of that spectrum is interesting. I'm going to come back to that when I look at the general case later on. Is this kind of shape here, where it appears to be flattening out at low frequencies. And the best way to look at that mathematically is by extending the omega axis to the negative axis. So what one gets is then a symmetrically shaped spectrum, which is the classical Lorentzian shape. That Lorentzian shape is the staple of linear resonance theory. Okay, it's not really very surprising that we get this kind of spectrum out of that system. Okay, so what have I established so far? Well, I've established that this model is physically plausible. Okay, and I've established that it has a spectrum that looks like this. Okay, as I vary the decay parameter here, the relaxation parameter here, this symmetrical kind of Lorentzian shape changes with its width changes. Okay, and its width is essentially a function of the dissipation rate of the system, and that's another important factor that I'll come back to later on when I consider the general case. Okay, so how does this model perform? All right, let's get critical. Let's actually look at the observations. Okay, so here I have on the left-hand side here two time series just pulled at random from somewhere around the world. And those time series perhaps contain 25 or 30 years of data. Defining the spectrum with 25 or 30 years of data is an interesting question. And I'm going to look at that in a little bit more detail in a minute when I consider the ENSO spectrum. Okay, so you could argue that that's not long enough to properly define or robustly define a spectrum. I'll come back to that in a minute. let's forget about that for in the meantime, and let's see whether this thing actually does the job. So here's the Lorentzian spectrum here, this straight line here, and here's the observed spectrum. You can see that the spectrum appears to jump around quite a bit, okay, but it does follow the Lorentzian spectrum quite well, I would argue. And I would also argue that a lot of this jumpiness, this sporadic behaviour here, is a function of the shortness of this record and nothing else. Okay? One can consider a more general setup, and what one can do is one can look at SST globally and decompose it into spherical harmonics and look at the behaviour of this spectrum with respect to the resolution of the spherical harmonics. And that's what this picture is on the right hand side here. So as the resolution increases, as the resolved scales become longer and longer and longer, we go along this axis here. This is the spectrum at the smallest scales, this is the spectrum at the largest scales globally. And it's very consistent. That spectrum of SST very much looks like the Lorentzian pattern over the full globe. At the largest scales, there seems to be some evidence that perhaps this might break down to some extent, but on the smaller scales, certainly not. I would say you would have a hard time rejecting the null hypothesis that Hasselmann's climate model. Yes?
How do you do spherical harmonics with things over land?
Oh, well, you set the anomalies to 0.
Do you? Oh.
Yeah. I'm not trying to be rigorous here. Okay.
Puzzled how you did.
Okay, so on many scales, this model seems to do a pretty good job, and I would have a hard time rejecting the null hypothesis that Hasselmann's stochastic model was wrong. The null hypothesis that it was correct. Yes.
Did you tune the spectrum with the K value? Is that how you tuned it?
That's correct. That's another good point. You can go back and you can ask yourself, well, what should K be? And you can argue on physical grounds that it should be of the order of 1 to 2 months to the K time, given the common mixed layer depth of the ocean. And that's what that value is there. But yes, it was tuned, certainly. Okay, so this is the Hasselmann model. And I would argue that this model appears to meet all 3 principles for stochastic modelling. Okay, and of course, as most people in climate know, this model has been extremely influential, probably for these reasons. Okay, so now let's move on to a generalisation of Hasselmann's model. And this is what I would regard as the minimal ENSO model. Okay, and I have to explain exactly what I mean by that because this is a rather controversial area. Okay, so as most people here know, ENSO is a coupled ocean-atmosphere phenomenon, and if one takes a whole range of different coupled ocean-atmosphere models and one linearises those models and calculates the normal mode spectrum of such models or the singular vector spectrum of the models, what one discovers is a rather interesting fact. It's probably not all that well known, and that is that that spectrum is very strongly peaked. So there are very few normal modes and very few singular vectors that are actually important to explaining the variability of ENSO. Okay? So what I'm going to do is make the most radical possible suggestion, take the most radical possible suggestion and assume that I can explain El Niño purely from the dominant normal mode. Okay, and then just add some stochastic forcing. Is that a reasonable thing to do? Well, as I said, the spectrum of normal modes in a lot of different coupled models is very strongly peaked in terms of the dissipation of those modes. So that's a reasonable thing. The other thing is that if you go to the observations of El Niño and you calculate something known as a principal oscillation pattern, then you find something very interesting as well. And that is that you get two dominant EOFs which couple into a principal oscillation pattern. Okay, and what do those dominant EOFs look like? The first, this is, sorry, I should be more specific, this is with respect to heat content or dynamical height within the ocean, which is thought to control the El Nino phenomenon. Okay, so the first EOF looks like something like that and something like that. Okay, and that's associated with the peak of El Nino, generally speaking. So whenever you have an El Nino or a La Nina, then you have a heat content pattern that looks spatially like this. This is latitude, this is longitude across the Pacific Ocean. Okay, then the second EOF looks like this. Instead of it being a wave number 1 pattern, it's a wave number 0 pattern centered on the equator, and it looks approximately like this. Okay, now there's actually a strong lag correlation between those two patterns. It's a very, very strong lag correlation, and it occurs at about 9 months. Okay, so what that's saying is that this pattern here leads that pattern there by approximately 9 months. And this pattern here was recognised in the mid-1970s by Klaus Wertke as the build-up phase of El Nino. So it's the precursor for El Nino. Those two EOFs taken together explain about 60% of the variance of the system, a large amount of the variance. And they're lagged with a lag of about 9 months. What's fascinating is that if you take a couple model and you do the normal mode calculation, the principal oscillation pattern analysis is the statistical equivalent of doing a normal mode analysis within the dynamical system. What one finds is that invariably the leading normal mode looks like that in the couple models as well. Okay? So not only does this complex mode here explain 60% of the variance, it's also the least dissipated normal mode within a range of different coupled models of El Nino. Okay? So it seems to explain most of the variance that's going on within the system. Okay, so how can I model that? Right, well I have one complex normal mode, so I need a two-dimensional system in order to build a model. Okay, and this I can represent here very easily. Okay, so what I have here is a series of parameters. This epsilon here is the damping rate. And then I have some stochastic forcing here. Okay, there's two timescales associated with this dominant normal mode. There's the damping time and there's the oscillation period time. And that's it. There's just two timescales. And then there's some stochastic forcing. What's the stochastic forcing? I'm trying to be very self-critical here. The stochastic forcing has been looked at extensively over the last 10 years or so, and one popular candidate for that stochastic forcing is convective transients in the tropical atmosphere. In a range of different coupled models, if you insert convective transients with white noise decorrelation timescales, then one can reproduce the observed behaviour of El Nino very well indeed. Okay, so there's a plausible physical origin for the stochastic forcing in this case too. Okay, now this is a very controversial subject because in the early 1990s a slightly different paradigm of El Nino as a stochastically forced system was introduced by Cecile Penland and co-workers. And in that system, there was a series of normal modes with different damping times, and as a result of those different normal modes within the system, singular vectors were important, on short timescales. And I'm going to come back to that at the end of the talk, okay? Whether this model's too simple or not, okay? In general, one could argue that there are other more damp normal modes within the system which are non-orthogonal to this leading normal mode, and they set up non-normality within the system, okay? And I've published papers saying that, so I'm not going to resile from that. The question here, though, is whether they affect the equilibrium spectrum or not, and I'm going to argue that they don't, probably. Okay, so let's look at the spectrum. All right, so as I'll demonstrate in a minute, I can solve this system analytically, and I can obtain various estimates of the spectrum for it. Oops, sorry, I keep pressing the wrong button. So these are various spectral estimates from that model, and what's happening here is that I'm varying the dissipation. So let's go back. So I'm varying this epsilon parameter here. Okay? So here are the various estimates, and you can derive that easily analytically. I'll come back to that in a minute, how I do that. All right, so and now what about the observed spectrum? Here's an interesting thing. How can we define the observed spectrum of El Nino? Well, I would argue that you have to be very, very careful about how you do this. Okay, the El Nino period is roughly 4 years, so I would argue you need probably a century's worth of data in order to get a robust estimation of the spectrum. I'll give you some reasons why that is in a minute. So what I've done here, this isn't my work actually, this is some work by colleagues, Keston et al. From Australia. What's done here is that 3 different indicators for El Nino, time series for El Nino, have been compiled with time series of around about 130 years each. So they're very long time series. They've been very carefully compiled. So what we have here is the faint line here is Nino 3, which is an SST index. We also have a rainfall index from the Central Pacific, and we also have the Southern Oscillation Index, which is the last two are atmospheric indices, and the first is an oceanic indice of the phenomena. And what I would argue is, based on 130 years of data, that the spectrum there is reasonably robustly defined. Okay, and it's actually, before putting this talk together, I did a nonlinear fit of these types of shapes here to that spectrum. And I played around with spectral windowing and so on. I found it extremely easy to get a very, very good fit for that observed data using this model here. Okay? And what came out of that nonlinear fitting exercise were estimates for both epsilon and for eta. And they were very robust estimates and interesting estimates too. So what I found was that the best estimate for epsilon was 1 on 10 months, plus or minus about a month. Very reliable. What's causing that is essentially the width of that spectral peak there. The width of that spectral peak is a function of the dissipation, very strongly a function of the dissipation within the system. That width is setting that 10-month timescale. And of course the period was about 4 years, as you would expect. What's interesting about that is that it's commonly believed from ENSO prediction studies that prediction skill is good for 9 to 12 months. And a study by Thompson and Battisti has revealed that that prediction limit is intimately connected with the dissipation timescale of such a system. So all of those factors square up with each other. Okay? You might ask, well, what about other spectral peaks that have been argued about in the literature. Biennial peaks, decadal peaks, and so on. And you can see here some evidence of peaks in various estimates of the spectrum, but I wouldn't like to say that any of those are particularly robust. And what's interesting too is that you can do a wavelet analysis with a sliding window of about 10 to 20 years and look at how the spectrum varies over the last 130 years. And what you find is what was alluded to in the first talk this morning was that the spectrum changes quite dramatically on decadal timescales. And for certain 20-year blocks, there are various peaks, and for certain other 20-year blocks, there are other decadal peaks. Okay, so what does that mean? Well, if I take this model here and I do the same thing, I get the same result. So if I take this stochastic model here and do a sliding 20-year window wavelet analysis, I get almost identical varying behaviour in the spectrum. What that tells me is that I need roughly 100 to 200 years of data to be confident about the spectrum. And if I try and make deductions on timescales of the order of 20 years, they're not going to be reliable. Okay, so that's one particular model, and you'll notice that it falls into this category as well. Okay, so a third kind of model. This model has been suggested as a model for decadal variability in the mid-latitudes. Okay, it was due to Saravanan and McWilliams, and it's been a very influential model in trying to understand decadal variability in the western boundary current regions of the mid-latitude oceans. And what you do with that model is that you build a channel. Okay, you build a channel along the eastern coasts, like the Gulf Stream or the Kuroshio, okay, and you assume that temperature anomalies are advected by those very strong currents, okay. And the other thing is that if you look at what the heat flux forcing is doing, and of course the heat flux forcing is a major control on SST, you find that the EOFs have very large scale structure associated with them. So this is the dominant EOF in the North Atlantic. This is the second EOF. This is explaining 26% of the variance. This is explaining 19% of the variance. The time series associated with those EOFs are essentially white. So these flux forcing terms here are essentially stochastic. Okay, so if you apply them to a channel model, okay, and then you do a Fourier decomposition with respect to the meridional coordinate here, okay, then lo and behold, you get exactly the same mathematical model as the El Nino model that I just went through, okay? And what's happening is that the stochastic forcing here, right, because it's got a wave number 1 structure, is only projecting onto one particular phase of the first Fourier component. The second one is projecting onto the other phase of the first Fourier component. Okay, so that actually mathematically is identical with this model here. It's exactly the same model. And but of course, such a system is harder to test, all right, against the observations, because what one's trying to do is explain a decadal peak in the data, and there's only about 150 years worth of data available. So if one relies on that 150 years of data, one's likely to get a non-robust estimate of the spectrum associated with this thing here. So this model's a little harder to check than the El Nino model, I would argue. Okay, so that's the preliminaries over with. Now let's go through the mathematics. Okay, so this is the system that I'm considering. Okay, and what I'm going to do is I'm going to calculate the spectrum, the equilibrium spectrum of that system in general. And what I'm going to do is I'm going to decompose it in such a way that it's obvious how it depends on the statistics of the stochastic forcing and how it depends on the dynamics originating from this A operator. Now, it's very well known in stochastic theory that, that such a system, the spectral matrix of such a system can be computed exactly. Okay, this is in Gardner, standard reference on stochastic differential equations, and it has this interesting form. Okay, this is the spectral matrix for that system. Okay, what you can see here is that you have A plus I omega, the identity, inversed. Okay, and R here is the covariance matrix for the stochastic forcing of this system. Okay, now if I want to play around with this and try and understand what's generating the spectrum, then I have to reduce this in some way. How can I do that? Well, I started by looking at singular vectors as a method of trying to do that and gave up. But normal modes work because in the normal mode case, if I change the basis for x to be a normal mode basis, and I can do that in almost all cases of interest, you can't do it if the eigenvalues of the normal modes are exactly identical. That's just a mathematical statement, but that's obviously not a realistic scenario. But in the case that you can find a normal mode basis, then this operator here, this matrix here, becomes diagonal, okay, and I can explicitly pull the whole thing apart. All right, this matrix over here is just the Hermitian conjugate of the other matrix operator here. So let's see what happens if I do that. Okay, well, also I want to familiarise you with what a spectral matrix means. What is a spectral matrix? What does that actually mean? Well, it means the following. If I take some linear combination of the variables from my model, okay, y is ci, xi, summation, okay, then the spectrum associated with y is simply this bilinear form here, okay? So this tells me how to calculate the spectrum of any linear combination of variables from my model, okay? So doing that, transforming to a normal mode basis, okay, I get this sum here, okay? And that sum is it's a double sum over all the normal modes within the system, okay? All right, where these QKs here are the complex eigenvalues of A. They're the eigenvalues associated with all the normal modes. Okay, so looking at this sum here, you can see that it consists of two parts. Okay, there's a diagonal part and there's an off-diagonal part. Okay, the diagonal part just refers to the spectrum of the individual normal modes. Okay, by just considering this here. Okay, and if I look at the diagonal part, it looks like the following. It just looks like that. Okay, so it's a Lorentzian. It's a Lorentzian shape. So the diagonal spectrum is Lorentzian. Okay, and there's going to be a contributor from each of the normal modes in this form here. This RNII is the covariance matrix of the normal modes in the normal mode basis. Okay, sorry, it's the variance in that basis. All right, so what controls the strength of that spectrum? That's interesting. So if I look at this here, you can see quite easily that at the peak, which is omega equals minus eta I, that the spectrum is 1 on epsilon I squared. So the spectral strength of the diagonal term here depends as 1 on the inverse squared of the decay time. Okay, so the decay time is crucial for understanding what generates the spectrum in such systems. Okay, so that's all the complete story if all one is interested in is the spectrum of normal modes. But of course one is interested in more than that. One's interested in particular linear combinations of the normal modes, and in that case the cross spectrum between different normal modes becomes significant. Now, what does the cross spectrum look like? Okay, well, by straightforward complex arithmetic you can manipulate the cross spectral terms. They're the k not equal to L terms from the sum that I just put up before, and you can write the cross spectrum in this very neat way. So it consists of the geometrical mean of the diagonal spectra, the spectra of the individual normal modes. This is the geometrical mean here. It depends on this FKL, which is known in multivariate statistics as the Wiener coherency. Okay, I'll come back to that in a minute. And finally, it depends on the cosine of something which is known as the phase spectrum in multivariate statistical analysis. So that's the cross term here. In this particular dynamical system here, the Wiener coherency doesn't depend on the frequency. It's a constant. And you can think of it as a complex, the magnitude of the complex correlation coefficient between the forcing acting on the various normal modes. It always lies between 0 and 1. Okay? And essentially, this factor here controls the strength of the cross spectrum. Okay? If that was 0 for whatever reason, then the cross spectrum would vanish. So when I come back to the specific example, I'm going to have to look at what the Wiener coherence does. Okay? The phase spectrum depends on three factors. It depends on the statistics of the forcing, it depends on the particular phase that I choose between the normal modes, okay, and it also depends on the dynamics. I'm going to consider this is a bit complicated. I'm going to consider this, go to a special example and show how this works for the El Nino case to try and explain this a little bit better. Okay, so let's go to the ENSO application. I've argued that that ultra minimal model could be applicable to El Nino. I don't want to place my neck on the line with such a statement, of course, but I would argue that you have to reject the null hypothesis that that model is covering most of the variability associated with El Nino. And I believe, based on my experience with coupled modelling of El Nino, that that's a hard null hypothesis to reject. Okay, so let's set this up, and let's assume that we have, let's go back to the model. Okay, so this is the El Nino model, where is it? So this is the El Nino model here. What am I going to do with these two stochastic forcings here? Well, what I have to do is I have to assume that there's some sort of possible correlation between those, and also that they have a variance ratio. And once I've done that, I've covered all possibilities, really. So that's what I'm going to do. Okay, so I've written that down. That's what I get for the covariance matrix of those two phases. Okay? But the two components in this model represent the orthogonal phases of ENSO. So they represent this phase here, and they represent that phase there, specifically. Okay, so what happens to the Wiener coherency in that case? Yep. All right, so this is what it looks like. This is the Wiener coherency. You can actually, I'm just drawing a plot of it. You can calculate it analytically, obviously, from what I've just done. And I've just plotted that analytical expression. And what I've got here is a plot of the variance ratio versus the correlation. And what you see is that Wiener coherency vanishes only if the correlation between those two stochastic forcings is 0, and the variance ratio is 1 between them. Otherwise, it's non-zero. Okay, so this is a very special case. It's hard to believe that the stochastic forcing for El Nino would lie exactly on that point there. Why? Well, if I look at what the physical origin of that stochastic forcing is, then one of the popular candidates for that are convective transients. Convective transients, as was shown in a beautiful paper by Wheeler and Colatis in 1999, have an interesting spectrum. Okay, this was what actually motivated this work in the first place, trying to explain that spectrum. And one of the features of that spectrum is that it's red in all directions. And there's no convincing explanation in the literature for why that is. So it's red in the zonal direction, it's red in the meridional direction, and it's red in the temporal direction. And no one really understands why. Okay, it's an unresolved question in convection, I would argue. So what does that mean? Well, if the spectrum is red zonally, that suggests that large-scale features are important to the stochastic forcing. And that would suggest that the correlation between F1 and F2 is non-zero. Okay, so I have a plausible reason for why the Wiener coherency is non-zero. Okay, I can also break up the phase spectrum, and this is interesting, into various pieces. The first piece is, this is the phase spectrum here. First piece here, theta 1, is the phase that one's interested in. All right, so am I interested in this phase here? Am I interested in that phase there? Am I interested in somewhere in between? That's what theta 1 is. Theta 2 essentially depends on the statistics of the forcing. It doesn't depend on frequency. And the final term here depends on frequency in a way which is a reflection of the dynamics of the system. So I've broken it completely up into those three pieces that I was talking about. The thing that's interesting is that this phase factor here enters with a factor of 2 in front of it because I'm dealing with the cross spectrum within a complex normal mode. That's a function of that fact. Okay, and in that case there, so what that means is that the cross spectrum changes sign as I go through 90 degrees. So as I go from here to here, the cross spectrum changes sign. So what does the cross spectrum look like? Well, you can guess already what the cross spectrum should look like from the functional formula I just gave you. Remember, it's proportional to the geometrical mean of the other spectra, right? And those other spectra for a complex normal mode have to be centered on plus or minus eta. Okay? So it's in between plus and minus eta because it's the geometrical mean between the two poles of the normal mode. Okay, so what does that look like? So what I've done here is I've plotted the spectrum at different phases at 90 degrees out of phase. And what you can see is the remarkable fact that the spectrum is most different at low frequencies. And the reason it's most different at low frequencies is because it's the geometrical mean of those two poles of the diagonal spectrum. Okay, and this is exactly the region which I would call, well, this region down here, I would call the decadal spectral strength of El Nino. Okay, so the conclusion of this is that if the cross spectrum is non-zero, if you believe the ultra simple stochastic model that I just went through, then the cross spectrum is telling you that there should be a decadal component to El Nino which is phase dependent. So one of these phases here is going to have more spectral strength at decadal frequencies than at other frequencies. And if you look at what the spatial pattern for the decadal variability of El Nino looks like, it looks like an SST pattern associated with this. Okay, with some other stuff in the mid-latitudes. So I would argue that this is a first-order explanation for the decadal variability of El Nino, and I think I'll finish there's some conclusions. Thanks very much.
Thank you, Richard. So time for some questions.
Yes.
Just a
Name,
comment. Yes, sir. Valerio Lucarini, University of Reading. Just a comment about the Occam's razor, which I think is very interesting. On the other side, I mean, the point is, if you use simplicity and, I may say, correspondence with observation as a criterion, without putting some, I may say, penalty, constraint, it is dangerous because you can just go back and saying, I use this model because it gives me a red spectrum, okay? Or then I could say, okay, I take a white noise with the same variance, and the second order is correct.
But I would argue that you have to look at other observable indicators to reject the null hypothesis.
Yeah, I mean,
I'm not saying that the spectrum should be the only constraint.
Yeah, I mean,
but it should be at least one constraint.
Yeah, but just continue. I mean, we have in model selection some criterions like I think one is the Akaike selection criterion. That is, you add another parameter, and if you see, and you check whether the added information, the added skill you obtain, is not something that becomes from a degenerate model. So I wonder if one should somehow state this explicitly, because there is the risk of just always choosing the simplest model which looks good. But I think it's a little dangerous. I'm not saying
no. I agree with you. I completely agree with you, and I think you have to take this philosophy advisedly. You have to look at a range of different observations, not just at the spectrum. So, for example, one should also look at the transient behaviour of the system. And I think in that case, for the El Nino case, you may be able to reject the null hypothesis. What I'm trying to argue here is that transient behaviour, which is due to non-normal growth, doesn't affect the spectrum because the normal modes associated, which cause that transient growth, have much stronger damping times associated with them. Okay.
No, just to comment on that. Oh, sorry, Michel Crucifié from Louvain in Belgium. Just to comment on that, it's a yield thing. It's how much you can get for how much you have to pay. If you can predict a lot of things for a very simple model, then it's probably fruitful.
Right.
I think this is one of the deep questions we might discuss actually in the next session.
Chris Farmer from Oxford. Have you been able to find, assuming if you look for it, a simple linear model that explains the EOFs that you use there?
Well, my rationalisation of that was that the EOFs correspond with the, if you use a dynamical coupled model, they correspond with the two components of the dominant normal mode from a range of different coupled models.
So
that's
you
my
need
rationalisation.
a complex model to get the EOF or
Yes.
a lot of data.
Yes, one has to use a sophisticated coupled model, and that's been done in the literature. It was done by Feifei Jin in the 1990s, and it was done by Andy Moore in 2002. Yeah, they actually looked at the spectrum, looked at the structure of the dominant normal mode, and it looks like that.
Stephen Belcher, University of Reading. Can you say something about the forcing? Because you've been talking as if it's external forcing, like weather or something like that. But as we heard earlier today, it can be internal non-linear dynamics. Is there a way of...
Yeah, that's a ongoing debate within the ENSO community. I belong to a camp that believes that a stochastically forced system is the proper perspective, but there are other people that believe that ENSO is a chaotic system. Okay, and in fact, what they find in certain models is that there's an interaction between this dominant normal mode and the annual cycle, and that interaction actually causes a broadening of the spectrum. Okay, so that's another explanation.
You use data to say something about the spectrum of the forcing to...
Right, well you're towing me into a controversial area now, so I'll nail No, my thing to the mast. What's the problem with that explanation is that it occurs in very few models. It's not very robust, and it's very sensitive to the parameter choices that one makes in the chaotic model. One has to sit on the boundary between various periods that occur within that space. So one can vary all the parameters within a chaotic model like that, and what one finds is that there are regular periods locked with the annual cycle, with periods of 1, 2, 3, 4 years, and that chaos occurs on the edge between those fixed, synchronized cycles. So you have to tune the model a lot to get that chaotic behavior. Okay.
Other questions?
Tim Palmer, I was just thinking that, I think you call it the precursor part of your ensome node is similar to what I think it was Tim Lenton was now referring to as the El Nino Modoki node, which seems to have become the preferred sort of quasi-stationary response to El Nino. Is that something that could be explained within the context of this type of model?
I'm not sure. I think it'd be interesting to look at actually because of the presence of stochastic forcing, when that particular phase of the system becomes significant or not, it might occur, at certain times. I don't know the answer to that, but it'd be an interesting question to look at for sure. Yep.
I have one more quick question.
Yeah, Jeff Alice from Princeton. Just to follow up on the previous question, I mean, those EOFs that you've drawn look so simple that you'd be surprised that you need such a complicated model to do it. I mean, you might imagine that there'd be a sort of a null hypothesis which would produce wave number 0 and wave number 1 as EOFs. I mean, you might consult with your colleague Ed Gerber, who's looked at it.
Another aspect of this is that if you go into the El Nino prediction game, what you find is a very interesting fact. That is that there's a very large range of different models, which include statistical models, which have approximately the same level of skill. And this would be an explanation for that fact. So in fact, you can build a statistical model based on those patterns and predict El Nino quite well. It's being done.
I think actually, time for a very quick one maybe.
I just wanted to make a comment. Oh, sorry, Aimé Fournier from NCAR. You commented that the red spectrum for the convective part of the signal implied the presence of large-scale organization.
Yes.
I wouldn't necessarily agree because a spectrum was also affected, as you know, by the smoothness of the pattern.
Well, what I think,
For instance, you
sure.
can take a triangle of any scale. And
Right.
it would have a red spectrum.
But if you look at the correlation at long distances, then there is a small residual correlation because of that redness. Okay, and that's all you need for this particular mechanism. I'm not trying to pin down a specific large-scale structural explanation. All I'm saying is that the statistics are such that a correlation over large distances is plausible. Plausible. Yeah, that's all I'm saying.
So I think we might call it a day. So thank you again, Richard, for a very interesting